Hi, I'm Gary Rubenstein. This is the 16th part of a series of videos where I go through math starting in kindergarten and working my way up through trigonometry. Last video I started on geometry, and it was more like philosophical about why do we even study geometry. And I made an argument that geometry is a study of proving things, kind of like being a lawyer, like logic, and it's not really about memorizing a bunch of formulas and applying them. You may not agree with that, but I think if it weren't for the proofs, geometry would have not really been worthwhile to be a year-long subject. Yeah, you'd learn a couple of formulas, and they could throw it into any math course. In the last video, I showed a proof that the so-called vertical angles, meaning if you have like a letter X, the angles that are pointing at each other, like 1 and 3, have to be the same measure. They look like they have the same measure. I gave a proof. I'm not satisfied with that proof because it was a little confusing. So I could do a better one. It would look like this. We'd say that angle 1 and 2 have to add up to 180 degrees because they make a nice straight line there. And over here, I can say, for the same reason, measure of angle 2 plus measure of angle 3 equals 180 degrees. So if both things equal 180 degrees, it would also be accurate to say that the sum of measure of angle 1 and measure of angle 2 would have to equal the measure of angle 2 plus the measure of angle 3. And remember from our algebra, if we realize to subtract stuff from both sides, in this case, subtract this measure of angle 2 from both sides, and what's left? And that's a simpler proof. Mathematicians call that proof more, believe it or not, they use the word elegant. Short and sweet. So I just wanted to show you that, another proof of this vertical angle. I wanted to give you the idea of what's meant by proof, and now we're maybe convinced that that's always going to be true, and then that becomes a theorem that I'm doing some more complicated thing, and I can use that. In geometry, we start with the most basic tools. In Euclid's Elements, the 5 like starting point rules are like the most simple things that you can connect any 2 points. You can join a straight line connecting them, or if you have a line segment, you're allowed to like continue it. Or if you have a line segment, you can make a circle that has one point as the center, and that the circle goes through the other one. Things like that. Or right angles always have the same number of degrees. Those are 4 of the starting points. The 5th one's a little confusing, and I'm going to simplify it to just say, remember the letter Z thing? Let's just say the 5th rule is that if you have one of these letter Z's where you have 2 parallel lines making the Z, that these 2 angles have to be equal. So from those like starting points, they build all this geometry and prove more and more complicated things. I think of it as like a toolkit where you start where all you have is like a rock and a stick, and then you use the rock and the stick to make like some kind of wedge, and then you use the wedge to eventually you make more and more sophisticated tools, and you prove the things. Like I mentioned in the last video, proof has recently sort of fallen out of favor, and people will say, well, we don't need to do proofs anymore. It seems like if that's true, maybe geometry should be shortened to a much shorter course, or the formulas should be incorporated into other courses if all we're going to do are a couple of formulas. Anyway, this video I want to tell you about what some of those sort of famous formulas if you're going to sort of know the basics of geometry, what those are. One concept that's pretty important in geometry is the idea of what's called similar figures. Similar figures is where you have two shapes where one is like a miniature version of the other. So yes, we have a big triangle and a little triangle, but these triangles are like the same proportions, the same sort of shape to them. We say that figures are similar if their angles are equal. So if somehow we know that even though this is a baby triangle and you got the big one, and then if these angles are equal, these figures are similar. And when triangles are similar, if this side was like 10 and this side was 18 and this side was 5, let's say, well, the miniature version would have the same proportions as the large version. So if like the 5 is half as big as the 10, then this other side, so-called corresponding side, would be 9 because it's half as big. Each side is half as big. So we say that in similar triangles, corresponding sides are in proportion. If we wanted to set it up with like an x there, we could say, 5 is to 10 as x is to 18 and solve for x. Now, similar figures can be used in the real world, like I have some tree here, and I don't know how tall it is, but I do know that its shadow at this time, that's the shadow, is 10 feet. So what I could do, I could imagine a triangle with the tree, the top of the tree, and the shadow there. This would be a right angle because the tree goes up. And then you could take a person, and we know that person is 6 feet tall, and we can measure that person's shadow. Maybe that shadow is just 3 feet. And because of the way the sun, because of the way shadows are formed by the position of the sun, this will create similar triangles. So I can go like this, 10, I don't know, 3, I do know. And I could say 3 goes with 10 as 6 goes with x, and solve for x. So we could actually work out the height of the tree using similar triangles. And there's a lot of other uses of similar figures. Here are 3 similar, well, all squares are similar. I've mentioned before that if the angles are equal, that's actually not enough. For triangles, it's enough, but for 4-sided figures, being similar it's not enough, because you could have a rectangle and a square that have the same angles but have different, their sides are not like proportional. Anyway, here's a square that has perimeter 4. When I double the side length, the perimeter doubles, and when I triple the side length, the perimeter triples. But the same is not true for the area. When you find the area of the first one, it's 1. The area of the second one is 4. And the area of the third one is not triple the area of the first, but it's 9 times. In general, if I have some kind of shape, whatever it is, and then I have a larger version of it, if this is, let's say this has width 5, and it has some area, let's say area is 50 for whatever reason, and if this one has a width of 15, the rule is that the area of the new one is the old area times, well, 15 is 3 times 5, but the area is not going to be 3 times the area. The area is actually going to be 9 times the area. And a good way to visualize that is to make a tic-tac-toe board here. At least for squares, we can see that a 3 by 3 square has 9 times the area as the 1 by 1 square. And that's like a interesting thing where a lot of people might think that if you double the sides, you would have to double the area also. But actually doubling the sides makes the area 4 times bigger, and tripling the sides makes it 9 times bigger. A big part of geometry, at least it used to be a big part of geometry, and if you took geometry a while ago, you'll remember this, but it should be, this is something that's important. I mean, I think if geometry is going to be a year-long course, the idea of proving that triangles or other shapes are congruent, which means they have exactly the same shape, same size, same angles. We used to spend months on this. I just want to remind you what they're talking about. Here I have 2 triangles, A, B, C, and D, E, F. They look like they're the same triangle, same shape, same size. But, are they? Well, if I handed you a ruler, you might say, I'll measure the sides 2, 3, 4. I'm just making up numbers here, but you might say, okay, I measured all the sides, so I know for sure these 2 triangles are exactly the same shape. But really that's not enough, because there's also these 3 angles. So then I hand you a protractor, and you start measuring the angles, and you say, okay, well, this is 40, and this is 110, and this is 30. Again, I'm just making these up, but so now I've measured all 6 things. At this point, is it enough to say that the triangles are definitely congruent? Well, yes. If all 6 pieces match up with all other 6 pieces, then the triangles definitely are congruent. But what if I'm not allowed to multiply all 6 things? I'm not allowed to measure all 3 sides and all 3 angles. Would it be good enough if I just measured 5 of the 6 things? What if I didn't know about this 30-degree angle? Well, it seems like that would still be good enough if the other 5 pieces matched up, because if the 40 and the 110 match up, that last one's going to be. What if I don't tell you the 110? How much is enough? Well, it turns out that if all you knew were the 3 sides and you didn't know anything about the angles, it actually would be enough. We call it the side, or the Sss Postulate. That says that if you know 3 sides but nothing about the angles, we can say that these triangles are congruent to each other if all 3 sides match up. It's also enough information if all I know is 2 sides, but I know the angle in between those sides. And that's called Sss Postulate. Basically means if you have 2 sides that are known, that match up with 2 sides in another triangle, and the angle between them are equal also, congruent, then all the other pieces are also. And the third one, that's the 3 sort of big ones, is what if I only knew 1 side? Well, that doesn't seem like enough information, 1 side. But if I have 2 angles, and if they're the 2 angles that are kind of formed by that side with another side, that's called ASA, angle side angle. It means that if you have a side equal to a side in another triangle and the angles around that side are also equal, then the whole triangle is. Those are the big 3. There are other ways. For instance, if I know 2 angles, if I have this 2 and I have the 30 Let's see what I did here. 240. If that's all you know, it's actually enough information, all that. We call it the angle side postulate. But that doesn't mean that any three things are good enough. Like if I just knew three angles, this is not drawn well because that's definitely not a 110-degree angle. But the idea is that three angles is not enough. AAA is not enough. But three angles is not enough for congruence, because we obviously here have a big triangle and a little one. But three angles is enough, in a triangle at least, for similarity. And in a sort of classical geometry course, you get these configurations with all these different lines, and they tell us okay, we know that this angle equals this one, and that this side from here to here equals this side from here to here. And they want you to go through all these steps to prove something, like prove that this triangle must equal that triangle. And it's hard. It's hard to do that. And you might wonder, why do we care about proving all these triangles equal to other triangles in these pictures that have all these lines in them? And the answer is that long ago, a sort of game that you would play with geometry is doing what it now calls, or even then were called constructions. Constructions is when you use a straight edge. A straight edge is like a ruler, except it doesn't have little markings on it. And a compass. Not the kind for north-south, but remember this thing? Has a little pointy end and has a little pencil there. Hopefully you can get these at any pharmacy or whatever. And using these tools, you get to draw stuff. And the question is, what can I do with a compass and a straight edge? And an example of something you can do, if you want to make a perfect equilateral triangle, you use your straight edge to make a nice line segment. Then you use your compass to make a circle. You open up the compass so that the center is on one end point and the pencil's on the other one. Then you lift your compass up and you do it again. You make another circle, but this time you make this other point the center. And let's say my original line segment was 10 centimeters long. If I take this point where the two circles come together, it's a nice looking triangle. It looks like it's equilateral, but is it? Well, yes, it is, because in a circle, every circle has a center, and if I go from the center to the edge of the circle, if one of them's 10, that's a radius, then all of them are going to be 10. So if this is 10, it's the radius of the circle on the left, that's 10. But this 10 is also the radius of the circle on the right, so that's 10. And this thing has to be equilateral triangle. So constructions, at least back in the day, BC times, the book Euclid's Elements is mainly, in my when I read it, a book of constructions, and then they use geometry to prove that the construction they just showed you how to do, that it did what it claimed to do. Just to give you the flavor for this, here's a random angle, and they say if you want to cut it perfectly in half, now you might say, of course I could cut it mainly in half. I do that when I get pizza sometimes. But they say if you have a compass and a straight edge, you make a circle. Then you make this line here. Then, using the construction from before, you make a nice little equilateral triangle going this way. And if you join this line here, what would happen is that we would get these two triangles. I'll make one triangle nice and green here. I'll shade it in. This green triangle and this red triangle. Well, what do we know about those triangles? Well, we know that this side and this side have to be equal because they're part of that equilateral triangle I just drew. We also know that this and this are equal because of they're both radii of the same circle. And this yellow line in the middle, well, that's part of both the red triangle and the green triangle. So using the so-called Sss postulate tells us that not only are these two triangles, it's not just the three sides that are equal, but all six things, the three sides and the six angles are equal. Well, one of those three angles, the three sides and three angles are equal, and one of those angles is this guy. So that would mean that this angle and this angle here have to be equal, and that means that this construction did bisect an angle. So these diagrams would come from like a construction, and then you would now constructions, which is one of my favorite topics to teach geometry, that has also been relegated to a thing that they stick at the end. Like, I mean, in Euclid's Elements, the very first thing is the construction of the equilateral triangle, but constructions got sort of squeezed out, and now we stick them in at the end of the course sometimes. And in New York State, they have multiple choice question about it on the state exams. So if we're not going to do constructions, if you're not doing constructions and you're not thinking about, oh, why did this construction work? And then you have to use the geometry proofs to prove the construction work. That's what geometry has been for thousands of years. But nowadays, they're being a little more informal with it. They might use some computer programs to like mess around with it. I think I have to make a video with another tool to show you what that looks like. I think that's what video 17 is going to be. Modern informal geometry and how they've modernized geometry a bit to get rid of the proofs and the constructions and make it a little more relevant or just modern, relatable. That'll be the next video. In an earlier video about elementary school math, I mentioned what pi was. Circumference is pi times diameter, which I mentioned means that if the diameter is this length here, and I try to like wrap it around the circle, one diameter won't quite be enough, two diameters around the circle won't quite be enough, three diameters around the circle won't quite be enough. We need this extra little piece here, which is about 1/7 of a diameter. And that number, that 3 1/7 diameters, 3 1/7 more accurately is 3.14159 going on forever, which we call pi. So pi is the number of diameters that go around a circle. And I mentioned that the area of a circle was pi times r squared. But I didn't tell you why that was at all. I wanted to spend a second to show you why should that be. If you take a triangle, and here's the radius, and I split it up into many, many, many skinny pizza slices. Their circumference is pi times the diameter, but the diameter is 2r. So we say 2 pi r. That's around the circle. Now if I take these slices and I rearrange them in a funny way, what each one is, one's facing up, one's facing down. It ends up becoming sort of a weird looking rectangle thing. And the height of that rectangle would be the radius of the circle, because here's like one of these slices has a radius as its like height pretty much. But its base is kind of hard to see. But take a look. The base, the sum of all the bases is 2 pi r, which makes each base pi r. See that? See if I make these little bumps here? All of these bumps together become the full circumference of the circle. But this rectangle thing, base times height, is pi times pi r. Pi r squared. The last thing I want to show you in this video, and then I'm going to do one more geometry video to show you, like, using graphics, what like informal geometry looks like nowadays. But as far as like, what do you need to know about geometry? What are like the main things that happen in geometry? I mentioned 180 degrees in a triangle. I just did pi r squared. But the most famous thing, the most famous math theorem that there is called the Pythagorean Theorem. Pythagoras was a Greek mathematician around 500 BC. And it's one of the most famous things in math. If you listen to like Gilbert and Sullivan, Modern and Major General, they mention theorem of Pythagoras. Pythagorean theorem says, as a formula, a squared plus b squared equals c squared. But what does that mean? People memorize that. That's like people memorize E equals mc squared, but they don't know, what exactly it means. And people, you say, what's the Pythagorean theorem? They go, oh, it's a squared plus b squared equals c squared. Well, what that means is that's related to, in geometry, if you have a right triangle. And you know 2 out of the 3 sides, and you don't know the third side. Well, the longest side, called the hypotenuse, is what's meant by C. And the other 2 sides, doesn't matter which one you call A, which one you call B. So we can use this formula as a relationship that would help us figure out the side by saying, well, A is 5 and B is 7, so 5 squared plus 7 squared equals C squared. 25 plus 49 equals C squared. 74 equals C squared. So C is not a nice number. It's the square root of 74. 70, which is between, it's like 8 point something. If I have a calculator, which I do, I can do the square root of 74 and see that it's about 8.6. So that's a relationship that it goes back even before the Greeks. In Egypt they had it. It tells us if we know 2 sides of a special triangle, right triangle, we can use it to figure out the third side. And that's true for all triangles, all right triangles. Proving that's true is actually very difficult. Usually it's done geometrically. They literally draw squares. And what the Pythagorean theorem says that these, if you were to like melt down this blue and red square and kind of pour it into a mold, it would have the same exact area together as the green one. And there's various like proofs of this, like there's hundreds of them. This is my personal favorite. You can see that the 5, they cut up this big square into 5 pieces, and they cut up the medium-sized square into 4 pieces, and like a jigsaw puzzle, they rearranged the 4 pieces, or the 5 pieces, to fit perfectly in here. That doesn't prove that it's always true, but it is a pretty cool looking picture. This is another one I like. Here, this is like the little one, a squared. Here's our triangle. We have like 4 copies of it. And here's b squared. Actually, we have 8 copies because we have 4 over here. And this is c squared. And we can see that this big square is composed of 4 of those right triangles plus a squared and b squared, whereas this other big square is also composed of 4 of those triangles and c squared. So if you take away the 4 triangles from both pieces, and assuming the big squares were originally equal, which is not obvious, you'd be left with a squared, b squared on one side and c squared on the other. But Pythagorean theorem is an extremely important and famous thing. And honestly, if there's only one thing you remember from geometry, Pythagorean. Now, yes, Pythagorean theorem gets used. You know, you can make up a word problem where somebody has like they have a ladder. You know, and they want this to be 10 feet. And they want to know, you know, and the ladder is 15 feet. And they want to know how high up on the wall does it go. I mean, that's not a really highly practical question, but I just did want to show you that in this case, the C was known, and the A or the B is not known. So a squared plus b squared equals c squared. A squared plus 10 squared equals 15 squared. A squared plus 100 equals 225. A squared equals 125. A equals the square root of 125. It's about 11.2. Pythagorean theorem is going to be the basis of trigonometry, which is the final video I'm going to make, which is looking like, I think, 21st video. I don't know. We're nearing the end because we're already getting to some pretty abstract math. Okay, so that was today's video. I took you through a simplified proof just to give you a feel for proofs. I said some more philosophy about like geometry and why do we do it and why do we need to do proofs. Opening up the question of if we're not going to do proofs and we're not going to do constructions, why do geometry at all? Why not just get the few formulas that are relevant and throw them into some of the other courses, take some topics out of those, save a year. But I'll show you in the next video some pretty cool things that with modern technology and computers, and we could actually make geometry more relevant. And it's something that I do in my classes a lot with some computer software. That's I'll look forward to making the next video. It won't just be me writing. There'll be a lot of cool, moving, animated computer graphics. So I hope I'll see you at the next video. Goodbye.